Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, everyone, I am on the line with Danny Stoll. Danny is a research assistant at the University of Freiburg in Germany. Danny, welcome to This Week in Machine Learning and AI.
Thank you for having me.
So, Danny, I interview a lot of folks that are practicing machine and deep learning professionally, as well as PhD students, but you are actually an undergraduate student working as a research assistant. And you've been doing deep learning since high school. How did you get introduced to deep learning?
So I guess it all started with a general interest in math for the math's sake. So I learned a lot about analysis and linear algebra, stochastics, things like that. And at some point, I got introduced to machine learning and deep learning via some blogs or things like that. And that really caught my attention. So I started with the infamous course offered by Andrew NG, a basic machine learning course. And when I worked on that course, which is an online course, I really got hooked. And I never looked back from that on and dove deeper and deeper, mostly using online lectures because at the time I was still a high school student.
Is that what you're studying at the University of Freiburg as well?
So the program I'm in at my university is a general computer science program. So we learn all the basics of that for sure. But there are a lot of mandatory courses which cover the basics. But in the later stages of this program, you have a lot of freedom. You can choose different courses. You can hear reinforcement learning, machine learning, deep learning. You can have different seminars. You can even listen to very advanced seminars. But what I did when I started this program, I joined the reading groups with the topics related to machine learning, and I joined the seminars just sitting in there, and I really enjoyed that.
And so the group you're in as a research assistant, automated machine learning, what's the focus of that group?
So as the name says, the focus is on automating machine learning because for once, it's not everyone has experience in machine learning. It's pretty hard to do, but a lot of people would like to use machine learning or even AI for their products, for their research. People that might not even have a background in computer science. So one goal of automating machine learning is to really democratize machine learning, to make it available to everyone. And you do that by automating it to really remove the necessary expertise to run machine learning.
And so we are going to talk a little bit about a paper you co-authored called Learning to Design RNA. Tell us a little bit about the origins of that paper and the problem that it sets out to address.
So I guess I should start with motivating why we care about RNA and what it means to design RNA. Many people or most people know RNA from their high school education and its role during the synthesis of proteins. But RNA can actually regulate biological processes directly too, much like proteins. And there's a lot of focus on proteins because they can regulate these processes. But RNA can actually do the same thing. And it has been connected to all kinds of different diseases like Parkinson's, Alzheimer's, epilepsy, and in a very recent study, also autism, which was a 2019 study. So we're even still learning about where RNA is involved, and it's only growing in size. So what actually matters about RNA in terms of which function it has in the body is its structure, its spatial structure, the way it folds, not the basic structure, which is just a sequence of 4 nucleotides. But you don't really know which kind of sequence the desired way. So once you can have designed a spatial structure that you would hope has a certain function in the body, you still need to design an RNA sequence which has this structure, which folds in the desired way, so you can actually have the desired function in the body. And that's what RNA design tries to address. So given a higher order structure, design an RNA molecule, a sequence, which has a structure, which has the function that you want to have.
And so it's the function determines the structure that you need, and the folding, the structure then determines the folding that's required to kind of create that structure?
Yes, it's the structure determines the function it has, and the basic sequence determines the structure, the higher folding. But we want to inverse that process. We want to go from function to structure to low-level structure, to the basic molecule itself.
Great. And so you kind of set out to tackle this problem. What led you to the particular approach that you ended up using here?
So, as we talked about in the start of this interview, our group focuses mostly on automating machine learning and deep learning. And one recent field there, or one recent approach, what people are doing is called neural architecture search, where you try to find the best architecture. You try to search over architectures of neural networks which perform best. And in the early times of neural architecture search, people used reinforcement learning and basically decided for each building block or for each stage in the network what you want to use. And we saw some similarities with RNA design, because there you also can choose which nucleotide at which point in the sequence you want to place. And that led us to try this out, and we got a proof of concept, and it seemed to work nicely. So from there on, we went with it.
Was there an existing body of research that you or kind of implementations that you were trying to automate through this neural architecture search, or did you have to come up with, I don't know if this question even makes sense, but did you have to develop the algorithm to do the underlying kind of folding?
Yeah, that's actually a great question. It's so there has been a lot of research into RNA design because it's such an important problem, and the research goes back almost 30 years. And you ask about the folding itself. Folding has actually been solved for RNA, and that's nice because if you compare it to proteins, there we are very far from solving folding. People are mostly working on folding, not designing. And so we had this folding algorithm available to us. It's called the Zucker algorithm. There are other algorithms, and our approach basically works with all of them. But we concentrated on this one algorithm because mostly everyone else was trying that as well. As for the state of RNA engineering before our publication, there were not many machine learning approaches. There were probably none that I know of. There was one other machine learning approach published in parallel to us. But before that, there was no really machine learning approach. What people usually did is they did a basic search, a local search, for example, to progressively improve the sequence that you have, that you want to then fold and see how well it folds, and then try something else at some sites of the sequence. But that does not work very well, we found, because it doesn't scale well with sequence size. What we did instead is we formulated it as a reinforcement learning problem and did it in a generative way. So we would put out the complete sequence that we want to fold at once, and then we learn to do that very quickly. And our approach scales really well with sequence length. Yeah, and the other machine learning approach, which was published, it basically implements a heuristic for a local search. So that's actually very different from what we have done.
And so what's the relationship between your use of reinforcement learning and neural architecture search here?
So in the early days, people were using reinforcement learning to do neural architecture search. So reinforcement learning is the type of learning where you get a state, or rather you have an agent and an environment, and the environment provides a state, and the agent can, based on the state, choose which action the agent wants to take. And what people did with neural architecture search is they said, okay, our actions basically choose building blocks for different layers of the network. Say, for example, would you want to choose a ReLU, or would you want to choose a different activation? Do you want a basic convolution, or do you want a separable convolution? Things like that. And we thought, well, let's do the same for RNA design. Let's choose which nucleotides we place at different points in the sequence.
And so are you using neural architecture search, or rather was this approach inspired by neural architecture search?
So it's both. So
okay.
We already talked about how our basic approach was inspired by it. But then we only had this basic idea, and it's a very novel setting for machine learning algorithms, and we didn't know what would work well. Which kind of architectures would we have to use? Would we have to use recurrent neural networks? Do we have to use convolutional neural networks? Do we need some embedding, which we learn, or would a basic embedding work? And we said to ourselves, okay, we could try these things by hand, but we're actually experts on doing this automatically and optimize it. And then we went ahead and formulated our approach in a general way, such that we could search the best architecture for it. But we didn't stop there. We also didn't know which kinds of hyperparameters we would need, how our training would need to work. And finding the right hyperparameters is a very tedious and time-consuming process, as probably all machine learning practitioners know. And our group usually tries to develop algorithms that automate this. So we used our state-of-the-art algorithms, our newest algorithms, and searched for the hyperparameters and the architectures jointly to really optimize for that. And we didn't even stop there. We thought, okay, but now we have to choose our environment. How do we need to choose our environment? What kind of reward do we need? How would our states need to look like? How do we need to choose our actions? Or what do our actions really correspond to? All these kinds of choices of the environment. And we also included these choices in our search. So we searched for the best agent and the best environment jointly. That's what we really did. And also the training hyperparameters. We really automated RL here.
I mean, it sounds like you kind of, threw the kitchen sink at this problem. You got a little bit of, it sounded like multitask learning in there, reinforcement learning, neural architecture search. When you're throwing so many, different cutting edge techniques at a problem like this, I'm wondering what are there some drawbacks or costs associated with doing that? Do you end up with, something that you wouldn't want to implement because it's too complex, or because there's no way for you to really understand what it's doing, or did you find that the result met all the criteria that you had for it? And maybe, that's a good place to start, is what are the criteria that you would put in place for a solution to this problem?
So one basic criterion that I try to follow in my work always is do it simple. You said we threw all these sophisticated things at it, but in actuality, our solution and even our automation is extremely simple. It sounds very complicated, but it's not. It's the final result is just a few layers. It's very basic. We didn't do any sophisticated techniques in there. Like, we didn't even have learning rate schedules, or we basically only experiment with basic convolutional networks, basic fully connected networks, different very simple embeddings, such that we could search over them efficiently. And also our automation is very simple. We formulated a 14-dimensional search space of integer parameters, like how many convolutional layers do you want, how many recurrent layers do you want, but also continuous parameters like what should the learning rate be, or how should we shape the reward? And we used a standard approach, or our approach for hyperparameter optimization, which is used in quite a lot of papers, and threw that at the search space. And look what came out. I guess a drawback when you do it like that is that you have computational overhead in terms of how because you have to search over these hyperparameters. You do that on many machines simultaneously. But I think that's the better way than doing it manually and have it cost developer time. Because a lot of bottleneck in machine learning and deep learning is not on the computational side, but on the developer time. And that's also a great problem that can be solved with this automated hyperparameter search and architecture search, removing the need for machine learning developers and researchers to really fiddle around with hyperparameters, because it is a very tedious and time-consuming process. And just formulate a search space, run a hyperparameter optimization on top of it, and see what works best.
And so were there any unique challenges or approaches that went into formulating that search space? Is it, as simple as the things you outlined previously, the number of layers and the types of layers, that kind of thing? Or were there interesting interdependencies, or, did you have to kind of craft objective functions in an interesting way? What was the kind of scope of that part of the problem?
So there were some things like the state space and the first few layers, which are conditional on each other. We have some conditional parameters there. But one other thing that we had to come up with, and that actually had a lot of impact on the final performance, is the way we do the reward. So what we do is once we have designed a sequence, we fold it, and then we compare the higher order structure with the one that we want to obtain. And then we take the distance of these two. But if you think about it, if your structure is 90% correct, then that's not really good, because you really need the structure to be exact. And then we had to reshape the reward to put a lot more emphasis on, if you only get 0.9%, if you only get 90% right, then your reward should almost be 0. But if you get 0.98 correct, then the reward, then there should be some reward, because they're very close. But we did not know how much we had to shape this reward in this regard. So we formulated the reward in a way such that we had one parameter which could influence this kind of shape. And then that's one part of our 14-dimensional search space.
With the reward function that needs to be shaped like that, I imagine that one of the challenges that you run into is that you're not able to give your agent enough information as to how well it's doing, unless it stumbles onto the perfect solution or something very close. Did you run into that challenge, and how did you address it?
So that's a major challenge. And when you start off with a single sequence and you run an algorithm on that, you might get very close and then you get some reward, yes. But if it's a very complicated molecule, then it's very unlikely that you will hit something successful. And that's a major drawback of algorithms before ours. But what we did is we incorporated this meta-learning or multitask learning across many molecules. So we could actually transfer knowledge from, for example, a simple molecule where we can get good solutions quickly to more complicated ones. So we can first learn the basics of the RNA folding dynamics, or the inverse of that, and then transfer this to some more complicated molecules. So that's also where a very great advantage of our approach lies in, because we can actually perform very well, very fast on very long sequences, which others cannot. And if you take this component out of our approach, which learns across these molecules, then we do not perform as well, but we would still have the state of the art.
And so is this transfer learning aspect, is this across different training runs, meaning you train up a model and then you apply it to a separate problem, or are you training across different problems or different molecules?
So it's kind of both, because what we do is we do a kind of multitask learning where we run on sequences, on RNA molecules in sequence and in parallel, and update parameters according to all of these RNA design tasks. And then we use the resulting parameters to initialize our approach on a novel RNA design problem. That's what we do. But what we also do is we explicitly optimize the hyperparameters, environment, and the architecture to do this transfer well. So we also optimize for being able to transfer well.
And how do you do that?
The objective that our hyperparameter and architecture search and environment search optimizes is, given a training set of RNA design tasks, and you can train on that, how well do you on a few novel ones? And we optimize this objective with our meta search.
And so when you kind of taking a step back and thinking about this from the perspective of the problem, the RNA design problem, what's your ultimate performance metric there, and how do you assess it? Is it are you comparing to other non-machine learning based approaches or something else?
We are comparing to the to non-machine learning based approaches that people proposed before us, but we're also comparing it to the one machine learning based approach that I also mentioned.
Mm-hmm.
And the kind of metric people used in the past for RNA design, and which we also adapted, is at each time point or for a given time, how many RNA sequences or how many RNA design problems rather can you solve? And solving means getting the structure completely right. And what people usually do is they say, okay, there we have a benchmark, there you get 10 minutes per sequence, or you have a benchmark where you get 1 day per sequence, and then compare only the final performance. But we looked at the complete trajectory of how long, at each time point, how many sequences have we solved. And what we can see, especially with our meta-learning or multitask learning approach, is that we solve a lot of sequences very, very rapidly. So for one of the benchmarks, we take some time for our parameters to load and everything, but after that, it takes 1 second, and we basically beat most of the other approaches, which take like 5 minutes to really solve this many sequences. So for one of the benchmarks, we achieve state-of-the-art results 1,000 times faster than the previous state-of-the-art. And for another one, we do it 60 times faster.
In this case of the 1,000 times faster, you said loading your parameters. Is that so? That's you're comparing a traditional approach that's non-machine learning based with just the kind of inference against your model?
Yeah, we run the inference of our model on or the complete time it takes for our algorithm to receive the sequence, to load the parameters and everything, and to start predicting something. So that's part of our evaluation. And if some other algorithms also need some initializations, then we measure that as well. Yes, but it's basically running the algorithms and looking at how quickly they solve a molecule, or if they solve it at all.
I guess I'm curious, when you're talking about 1,000 times faster, is it, are we really at that point trying to compare apples and oranges, or are they really comparable in the sense of a lot of your work is done in training, and then you produce this model that is, once you've got the model, the time it takes to get the inference is going to be much less. Whereas if you have an algorithm that's doing the computation at the time of, trying to figure out the answer, it strikes me as not being particularly comparable. Am I thinking about that correctly, or?
Yeah, you can think about it that way, but that's actually a nice thing about our approach, that once you have trained it, which doesn't take a lot of time, in our case it took an hour or 3 hours, and once you have that, you can apply to novel RNA design problems, which you haven't seen before, and it just works. That's definitely something that you should aim for. Mm-hmm. Like if you can pre-train your model or your algorithm beforehand and can make use of information that you have for other problems and apply it to new problems, then that's a very nice thing.
Right.
And we also have one instantiation of our algorithm which does not do that, does not transfer knowledge, but just runs at the problem directly. And that also achieves state-of-the-art performance.
I mean, in one sense, that it's saying, a machine learning approach is where you produce a model and you can run inferencing against this model is better than an analytical approach where you're kind of doing the computations from scratch every time. But you're saying that because the algorithm, because your model generalizes, it's kind of a valid comparison.
Yes, that's what I'm saying. And there's also the other machine learning approach that I talked about, which also uses reinforcement learning, but it only implements a heuristic via the reinforcement learning for a local search for these more traditional methods, and transfers knowledge for that as well. But I'm not sure how well it actually does that. Yes, but and it still cannot just generate a sequence from scratch directly, which works. Yeah. Mm-hmm. And so from my point of view, being able to transfer knowledge from a set of training tasks to novel tasks and make the performance better is a great thing. But I might be biased since a lot of my work also focuses on meta learning, where you try to do the same thing. You try to learn, or you try to learn to effectively solve novel tasks.
If someone's listening and they hear this and they want to try it, are there particular things that they need to be aware of or think about that are specifically related to maybe any interactions that all these things have with one another? Or are they pretty straightforward to apply in conjunction with one another?
So because what we did is very simple, we didn't run into really a lot of problems with using all these things in conjunction. But if you want to combine very sophisticated meta-learning algorithms with something like neural architecture search, that's a hard thing to do. And that's an open research question. How do you effectively meta-learn to do architecture search, or how do you do architecture search for meta-learning? That's what people are researching. But in our case, it was a very simple thing, a very simple formulation, which ended up working great. And that's also a strength of our approach. That it's very simple. It's using hyperparameter search and architecture search and all these things. But the way we formulate it basically reduces to hyperparameter search for all of these things. So we formulate a neural architecture search as a hyperparameter search. Mm-hmm. And the same with the environment. And that way you can very effectively search over all these choices at the same time. And we talked before how we explicitly set the objective of our optimization for to how well the configuration transfers. So that's a thing you can do as well. You can explicitly optimize for how well your meta learning optimizes, or how your multitask learning transfers.
In the paper, you talk about some ablation studies that you did. Can you talk a little bit about those?
Yeah, sure. So in general, I think it's very important to do ablation studies for your systems, for your algorithms, because if you do not, you do not know what actually is the thing that performs well. And if you do not do an ablation study, then you end up doing things that don't help, and that just makes your approach more complicated. And more complicated for other people to use. So I think in general, it's very important to do an ablation study. And what we did is we ablated, or we disabled the meta learning, the transfer learning across molecules, learning across molecules. And what we observed is that while we still achieve very good results when we compare to other methods, we do solve things much more slowly, and also solve some molecules not at all. One other thing that we disabled and saw how important it was building a model itself. Like, do we actually need to build a model, or is it fine to just randomly predict something? And as you would expect, that does not work very well. Yeah, we also had an additional step in the reward, or in the folding, where once we are very close to a solution, like only 4 sites or very small number of mistakes were made, then we do some more search for it, like not go through our reinforcement learning agent again, but just try some things, just change some things and see how it affects the folding and if we can solve it. And in early stages of our approach, that was very important. So we kept it in there. But once we optimized for the transfer learning and everything, we observed that its importance got less and less. And only on very hard problems, on very hard RNA design problems, it does make a difference. So we ended up using that because it does help in these very hard cases. But we could have disabled it for easier benchmarks as well. And that's something we learned from our ablation study. That's very important, I think, to really learn what difference do your components make of your algorithm. What happens if you disable them? Are they really critical? Do they help at all? And people do not do that enough, I think.
Mm-hmm. Did you develop any intuition for why that particular component only had the impact with the more complex molecules?
That's a good question. I don't have a good answer, I guess. That's not something we have looked too much into, because only at the very late stages we found out that it's not actually important anymore. So our intuition before that was like, our model predicts a complete structure and it has to get everything right. But our model is also very stochastic. So it basically learns a distribution over molecules, and you can make some mistakes there. And we added this local adaptation step to really make up for this generative approach where you and allow the model to make some small mistakes. That's how we thought about it. But once we got a very good model and really learned how to transfer learn here, we then observed that it did not make that many mistakes anymore, and it was more certain as well in which areas of the molecule space it wants to predict. So it basically did this kind of search itself. That's how I would interpret it, I guess. But for hard cases, then for very long molecules or very big molecules, it cannot do that very good still. So there, you still want to allow the model to do some mistakes and help it explore around good regions, I guess.
One of the themes that comes up in pretty frequently in my interviews is this pendulum swinging between traditional model-based approaches to the world where we're solving problems like this based on chemical or biological principles to more of a statistics-based approach, and how in a lot of research the pendulum is kind of centering again, where we're trying to marry these model-based approaches with the statistical-based approaches. Is that something that you could see an opportunity for here?
So your question is whether the more traditional approaches for RNA design can be married with something like our approach in the future to even get better performance?
Essentially, yes.
So, so I see potential in using our agent to produce a good initial guess for how the molecule should look like, and then use more traditional methods to then work with this initialization. Because a lot of the drawbacks of these traditional methods, which are mostly search-based, are that it takes a lot of time to get close to a good solution. So if you can already get very close to a solution right from the start, like using our agent, then the drawbacks of the traditional approaches might not exist anymore. And I see a lot of opportunities there.
Thanks so much for taking the time to chat with me. It was great chatting with you about this stuff.
It was my pleasure.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. Make sure you head over to twimlcon.com to learn more about the TWIMLcon AI Platforms Conference. As always, thanks so much for listening, and catch you next time.